Hello, everyone. My name is Sebastian Rodriguez from Wolfram Research, South America. I'm part of the Wolfram Quantum Framework team. I work as a researcher and developer in quantum computing, focusing on variational algorithms and their application to optimization problems. For this presentation, we will talk about symbolic quantum classical optimization, also called hybrid optimization. In specific, we will be talking about the quantum approximate optimization algorithm applied to the max-good problem. Wolfram Mathematica is widely known for its symbolic computation capabilities, and the Wolfram Quantum Framework extends that power into quantum computation. This makes an ideal environment for designing, testing, and analyzing variational quantum algorithms like the quantum approximate optimization algorithm. So let's start. We will be talking about first about the max-good problem. So let's start with the max-good problem in the classical formulation. So the max-good problem is a combinatorial problem where, given a graph, the objective is to find a partition that maximizes the number of edges between two different set of nodes. To make this a bit more formal, the max-good problems involve partitioning a graph set of vertices B into two disjoint subsets, aiming to maximize the number of edges connecting nodes in different subsets. Mathematically, we can represent each vertex with a binary variable +1 or -1 and formulate a cost function that assigns a contribution whenever an edge is cut between the two sets. So let's check the formula for the classical formulation. I find it easier to grasp the cost function formula if we first tag each of these nodes 1, 2, 3, and 4 using +1 or -1. Then when you apply the product of Si and Sg in this formula, you can easily tell whether an edge is cut by seeing if their values are different. If they have the same sign, meaning the nodes weren't separated, no contribution is applied. For this first example, our goal is to maximize the number of nodes placed into different sets. If you count the edges we are cutting in this example, you will notice that we are cutting 4 edges, which is the maximum possible in this case. So, to solve this in a quantum computer, we use the quantum approximate optimization algorithm, or also called QAOA, shown here as a quantum circuit alternating between two main ingredients. First, the cost layer, and then the mixer layer. In the quantum version, we represent these binary values as 0 and 1 instead of +1 and -1, and each node corresponds to a qubit. Our goal becomes now finding the bit string state, like this get state 0, 1, 0, or the analogous 1, 0, 1, with the higher probability, which in this case would represent the best partition. Now it's time to talk about the quantum approximate optimization algorithm. So the quantum approximate optimization algorithm, which I will be referring as QAOA, is a well-studied approach for solving combinatorial optimization problems. First proposed by Edward Farid as a variational quantum algorithm designed to find approximate solutions to the max-cut problem and to be executable on near-term intermediate scale quantum devices, also called NISQ devices. So the QAOA was formulated as a variational approach that alternates between cost and mixer layers. The central idea is to encode the objective function of a combinatorial optimization problem into a cost Hamiltonian, and then variationally optimize the parameters to search for an optimal bit stream. So now the QAOA involves the following steps, one by one. First, we define a cost Hamiltonian HC. This Hamiltonian is designed such that its ground states encodes the optimal solution to the combinatorial optimization problem. Then we define a mixer Hamiltonian. This Hamiltonian is used to explore the solution space by driving transitions between different states. Then we define the unitary gates using these Hamiltonians, and then applying it alternatively in layers, forming this following unitary depending on gamma and theta. So now we will prepare the initial state, which typically is a superposition of all possible states. Then the alternating application of UC and UM evolves this state according to the chosen parameters. So finally, we'll be optimizing the parameters and at the end measuring. So classical optimization techniques are used to adjust the parameters gamma and theta to maximize the expectation value of the cost Hamiltonian HC. The measurement of the final state provides an approximate solution to the original problem. So now, let's dive into the intuition behind the answers for the Max-Cut problem. QAOA quantum circuit is conformed by a layer of parametric RCC gates, which are built by the control nodes and rotations in C, and a layer of rotation in X as a mixer. I have to also mention that we have a superposition layer in which we initialize the system. So since the Wolfram Quantum Framework works symbolically, we can inspect each circuit operation. Don't forget to load the Wolfram Quantum Framework and also load the quantum optimization packlet. You can also click on this link and it will send you into the website with the documentation about quantum optimization in the Wolfram Quantum Framework. So to implement the Max-Cut on a quantum computer, we begin by placing all the nodes into a superposition, which ensures that each qubit has an equal probability of being in either of the two partitions, let's say A or B. So this is achieved by applying a Hadamard gate to each qubit, allowing the system to explore all potential partitions simultaneously. One intuitive approach is to look for a periodic bit string pattern, such as 010 or 101 as the previous example, since this will indicate that neighboring qubits are being separated. So we can start applying a sequence of gates as the control node, the rotation C, and other control nodes, which will differentiate periodic and non-periodic bit strings by applying correspondingly a positive or negative exponential function to them, as you can see in the formula here. This gate is also called RCC, in case I didn't mention it before. So now we can observe this differentiation better in the amplitudes plot by comparing a regular bit string versus a periodic bit string. But this is way more obvious when checking the probability plot. When one solution probability is in its peak, the other is almost disappear. So, however, this previous step doesn't fully explore all possible cuts, as some amplitudes remain unchanged. To ensure we explore all configurations, we introduce a mixer layer to facilitate transitions between different states. In this case, we will use rotation in next layers. This dramatically enhances the expressiveness of the circuit. As you will see in the next plot, this adds an extra dimension, creating a landscape of peaks and valleys, helping us better navigate towards optimal solutions. So now we are ready to move into an example, a 6-node graph. So first, to solve the max cut, we need to define the Hamiltonian representing the system. As you can see here, we represent which qubits are connected in the graph by the C operators using strings and then applying summation between them. This is easily understood by the quantum operator functionality from the Wolfram Quantum Framework. So we proceed to implement the cost Hamiltonian with it, using it. As you can see here, I have calculated this string, summation of strings, and then put it inside the quantum operator. So then we directly implement the QAOA circuit using the graph functionalities. In this case, we are mapping the information from the graph vertices to the qubits from the quantum circuit. In this case, as you can see, we can use the quantum circuit operator, the vertex list to set the nodes as qubits, and the edge list to indicate the connection between the nodes in the graph. So now that we have already implemented our circuit, we then implement the symbolic cost function using the cost Hamiltonian that we calculated and the resulting parameterized state from the previous circuit. We are basically getting a mean value here. So now that we already have the full expression of our cost function symbolically, we can maximize the cost function and obtain the optimal parameters using n-maximise, as shown here. One key advantage of this approach is that we can use any classical optimizer, not just those built into Mathematica. So now we obtain multiple possible solutions. However, with just a single QAOA layer, we observe 4 solutions with high probability. Now we are going to solve it classically and then analyze the 4 most probable quantum solutions indicated by the probability plot. Following the labels in the vertexes, the solution, the 3rd solution and the 4th solution, which are analog, are the ones found by the classical method. And this will be like the diagram corresponding to the solution. So now let's move into QAOA-in-QAOA. To tackle large graphs, we use a method called QAOA-in-QAOA, inspired by the divide and conquer algorithm. Here's the main idea. First, we have a huge graph, and then we partition the graph into smaller subgraphs. That's the ones colored here. Then we solve a mini QAOA, let's call it that way, on each subgraph and combine the solutions. Then, to correct any possible issue with the solutions between the subgraph, we treat each subgraph as node in a new coarse-grained graph. So then, finally, we apply QAOA again to this higher level graph and correct the final solution. So this process is recursive and scalable, making it suitable for large problem instances. So now let's see how the Wolfram Quantum Framework enables us to symbolically model and analyze this algorithm. We start with the divide phase. First, we load the Hamiltonian for each minigraph, as you can see here, using the strings for the Pauli matrices. Then, we construct the symbolic QAOA circuits with qubit indices mapping directly to graph nodes. Remember that we have one circuit per each subgraph here. The main idea, as I mentioned, is to have circuits that without much qubits in order to solve the problem by parts. So after simulating the states, we can observe how the symbolic computation can give insights about cost functions for each subgraph. We can visualize the parameter space using contour plots, giving us deep insights into optimization behavior. We can even see the equation for each cost function of each graph. Then we can move into the optimization process using n-maximize for each cost function and obtain the probability plot for each solution. After running one QAOA layer on each subgraph, we already obtained partial solutions represented by color nodes in these graphs, yellow and red, which are like the partition A and the partition B that I mentioned before. As you might notice from this latest graph, the subgraph solutions generate penalties when connected. For example, notice how the yellow edges connect almost 5 nodes. In order to prevent that to happen, we need to move into the conquer phase for global correction. So in the conquer phase, we construct a new graph where each node represents a subgraph, and the edges are based on their prior connections. We assign weights to these edges based on the connections between subgraphs, and then apply QAOA again on these higher level graphs. So here we build again the circuit following the same step from before. We only have 4 qubits here because we have 4 big groups, big subgraphs. Then we obtain the symbolic cost function. And finally, we run the optimization. So now we observe the resulting probability distribution and solve the max cut problem for the higher level graph. Here we have a yellow line here, which is referring to the groups connected here, the group 2 and the group 3. So in the final step, we take the subgraph that are yellow nodes, in this case 2 and 3, in the higher level graph and flip their node values. For instance, in some subgraphs, yellow nodes may become red as the global optimization balances local and global constraints. You can see this in this graph here. We have all these connected yellow lines here, but as you remember, the 2 and 3 got their values flipped. So now the ones that were yellow are red, and we disconnect all of them now. We also disconnect this group of red nodes here too, as you can see here. And that will be all for it. Thank you very much for your attention and to be present here. By the way, I left some QR codes here. This is my personal webpage where I show all what I do in the Wolfram Quantum Framework and complex systems. And also here is a QR code for a computational book as an introduction to quantum optimization, which I think is ideal for people introducing to quantum computing and also people who have engineering background on it. Thank you very much. These are the references.